So problem one for today is called reverse nodes in K group. But before that, we'll take a look at problem two, that is palindrome linked list. So what is a palindrome? Everyone knows what a palindrome is. A lot of questions you might have solved on checking whether a given string is a palindrome or not, correct? So what is a palindrome? A palindrome is a string which reads the same from the back and from the front. For example, the word Nitin, Nitin. Its letters arranged backwards or forwards will give you the same data, right? Nitin only. So that is a palindrome. And they've asked us to find if a given linked list is a palindrome or not. How do we check for palindromes normally? Forget the linked list part of this. If it was a string, how would we check if it is a palindrome or not? We check if, we can check if a string is a palindrome in a really simple way by using the reverse function and reversing the string, and then we can compare the original string and the new string and checking if they are equal or not. If they are indeed equal, then that means that the palindrome, the string is a palindrome. Otherwise, the string is not a palindrome. But that would take extra memory, extra time also. So we can do it faster and better by comparing the first letter and the last letter, second letter and the second last letter, so on and so forth. If we do not encounter any letters which are different, that means it is a palindrome. Otherwise, it is not a palindrome. If suppose the string A, B, C, D, E, F, we'll first check A and F. That A and F are not the same, so it's not a palindrome. So we know we can solve the problem if we have a string, right? So one approach, the first approach you can think of in this problem would of course be to convert the linked list into a string and then check if that corresponding string is a linked list or not. So that is a very simple approach, and that's why you can see the problem over here is mentioned as easy. So how would you code that out? For example, it would be simply traversal, right? You could, for example, over here declare an empty string s, and you could traverse the linked list. Suppose you could have a node p over here. You could have node p, and p not while p not equal to null, you could keep traversing and keep adding s plus equals to p's data, correct? This would give you all the numbers in the linked list converted into a string form. Now you can simply use another approaches we discussed before, check if the string is a palindrome or not, and that will give you your answer. But that approach is not really very good, right? It might be very fast, of course, O of n time complexity, but notice that you're using extra space. What is that extra space you are using? The extra space is a string which has n characters, where n is the number of nodes in the given linked list. So if you give this, suppose you are in an interview, the interviewer asks you this question and you give him this approach, he will for sure ask you to make it more space efficient. He'll ask you to reduce the space complexity. Over here also in the question, you can see the follow-up. Can you solve this problem in big O of n time complexity and O of 1 space complexity iteratively? So yes, we can do that. Let's take a look at how we can do that. So if we want to solve it without any extra space, that means we'll have to use the linked list only, right? We can't use any other extra external data structure, right? So how do we check? We'll use the same approach. There's only one way you can check if it's a palindrome or not, right? Like two ways, like I mentioned, but O of n time complexity without using any extra space, there's only one way. You'll check the first element and the last element, you'll compare them. They are the same, you move on to the second and the second last, they are the same, and so on and so forth. Unless and until you run into an element which is not the same, in which case you'll return false, that it is not a linked list. And if you don't run into any such case, that means it is a linked list. But what is the problem? Why can't we use this approach? Because over here, notice it's mentioned that it is a singly linked list. Can you traverse backwards in a singly linked list? You cannot traverse backwards in a singly linked list, right? A singly linked list, may traversal backwards is not possible. So how do we overcome this problem? So think of an approach we used a couple of problems ago, a couple of days ago. That approach involves reversing a linked list. How do we, why would we reverse a linked list? Because traversing a reverse linked list is the same thing as traversing a normal linked list backwards, right? So instead of traversing from front to back, from back to front in a normal linked list, we can simply reverse the linked list and traverse from front to back. But notice you need to compare the first one to the last one and second to the second last. That means we don't need to reverse, we don't have to reverse the entire linked list, right? We only need to reverse the latter half. So half of the linked list has to remain as it is, and the latter half has to be reversed. So how would we do that? Let's break it further into some sub problems. To reverse the latter half of the linked list, first we need to find the middle of the linked list. So, of course, we have solved this problem before, finding the middle of a linked list. The normal way to find the middle of the linked list would, of course, be finding the length of the linked list. So you'll iterate over it. You'll keep adding the number of nodes into your variable, suppose n, and then n by 2 nodes would be your middle node, correct? But as you've seen before, there's a faster way to do it, only in one pass by. That is called the tortoise and the hare algorithm, or the slow and fast pointer algorithm. So what exactly is that algorithm? For those of y'all that do not recall, in that algorithm, the slow and fast pointer are pointers which point to head, and the slow pointer moves one node, and fast pointer moves two nodes. And this continues on and on until fast next is not equal to null or fast next is not equal to null. So how does this work? Since fast moves double the distance of slow, while fast reaches the end of the linked list, that means slow will be at the middle of the linked list, right? Let's take a dry run so you can understand it better. Let me just get rid of these annotations. Give me a second. Yeah. So let's go through a dry run. This is the linked list we have been given to check whether it's a palindrome or not. So we'll follow the steps. What we need to do is reverse the latter half of the linked list, right? So this is the latter half of our linked list. So we need to reverse this part. So we need to find the middle for that, correct? So for the middle, as I said, fast and slow pointers both point to head. Fast moves by two positions. It was at 1, it went to 3, as you can see over here. And slow went from 1 to 2. Then slow moved on to 3. Fast again moved 2 places, went to 2. And now a while loop condition is false, right? Fast's next is indeed equal to null. So we will say that we will break out of a loop and we'll have slow as the middle node of our linked list. You always want the node before the middle node, right? Because the entire latter half will be reversed. So this slow is at the perfect position. Now comes the next part of our algorithm, reversing this linked list. We have a pointer to this node, we have a pointer, so and we have this list to be reversed. It's very simple, right? We all know how to reverse a linked list. So this node 3, we'll maintain 3 pointers. Previous, which will be denoted by P, for example, previous, or previous will point, okay, there'll be, this will be a current, this will be previous. And at the start, actually, we maintain previous as null. Do you know why we maintain previous as null? Because 3 eventually, after reversal, will become the end of our linked list, right? And the end of the linked list must always point to null. So what we'll do is we'll maintain this as next, and this link will be broken. This will become previous. This link will now point to previous, and now we'll update. We'll move on. Then we'll move on to 2. Our previous will be updated to 3, right? So 2 will point to previous. Our next will be 1. So we move on to next. This will be pointed to previous. And our linked list is reversed. Is our linked, this latter half of the linked list is indeed reversed. But there's some problem over here. Can you notice it? It's that this part of the linked list is now disconnected, right? So we need to make this join for our linked list to be in the desired form. So how do we make this join? This join can simply be made by saying slow, which is 3, slow's next is equal to previous. At the end of a while loop, a while loop continues on until current is null, correct? So if a current is null over here, then a previous will be the last node of our linked list, correct? So we'll simply do slows next equals to previous, and the linked list will successfully be reversed. As you can see, this linked list gets turned into this. Over here you can read these visuals I found on the internet. Very nice they were, and very explanatory. So this is the code. Okay, so now before I go on to the code, I'll just go over the last part too. Now we have the linked list, right? So we'll simply move slow to slows next, because we need to start comparing. This is the first element which you have to start comparing head with. Then 2 will get compared with this element, 3 with this element, of course. So our slow was originally here, as you can notice. We move it one forward, and we have a pointer over here. In the visual they've given a new pointer dummy, which points to the start of the linked list. But notice that to save memory, we do not need to do that. We can simply reuse the fast pointer. Now reinitialize it to dummy, and instead of moving 2 nodes like it did before, we'll move 1 node and we'll check. Is dummy equal to slow? Yes, it is. Let's move on. Is dummy equal to slow now? Yes, it is. Move on. Is dummy equal to slow now? Yes, it is. Move on. So we keep moving on, and then we'll move on again, and now our slow will reach the end of the linked list, right? Slow will become null. So that means we have checked all the elements. No need to check anymore, and that means that we reach the end of our linked list. And since we had all the elements equal, it means that this linked list was a palindrome. So there we go. If of course, if one element over here is different, suppose this was 4, so it would check 4 with 2, it would see that it's different and it would return false. So that is basically the logic. Pretty simple to understand. It was a combination of all the previous concepts that we had done. So here's the code. As I explained, I declare 2 pointers, slow and fast. Slow and fast say I find the middle node. Previous cur and next. This is used for reversing the linked list. Next is equal to cur's next. This is initializing the next pointer. Current is set to the previous. And now we have to move on to the next node, right? So previous equal to current, and current equals to next. So slow is next equals to previous. Slow equals to slow is next, because yeah, this is reinitializing the link. As I told you all, it was making this link slow equals to previous, and slow is next equals to previous. And of course, now to compare, we need to move slow equals to slow is next. If you're getting confused with the naming and all, you can declare 2 new pointers, first and second, for the comparison part. But to save memory, I've just reused my slow and fast pointers. No need to get confused in that. And there we go. That is the solution. So as you can see, this code passes. It is quite fast too. It performs better than 98.58%. So that was problem 2, palindrome linked lists. It goes over some very, very important concepts, revisits them. We have already seen them in previous discussions. Okay, so let's move on to the other problem for today. Reverse nodes in K groups. This problem, as you can see, is a hard problem. 30% success rate, 56 minutes is the average time to solve. So yeah, you can consider this one of the hardest problems you can get with respect to linked lists. What does it say? You are given a singly linked list of integers and an integer array B of size n. Each element in the array B represents a block size. Modify the linked list by reversing the nodes in each block whose sizes are given by the array B. So this is yet another reversal problem. But notice over here, we don't have to reverse the entire linked list, or like in the previous problem, reverse half of a linked list. The linked list, the number of nodes to be reversed are mentioned in an array called array, which is has the name B. So if there's the array is 3, 4, 5, you have to reverse the first three nodes, then connect it to the reverse part of the next four nodes, then reverse five more nodes, and so on and so forth. And notice over here the condition given is, if we encounter a situation where bi is greater than the number of remaining nodes in the list, we simply have to reverse the remaining nodes in the block and ignore all the block sizes from b of I. What do I mean by this? What do they mean by this? Basically, suppose our linked list had suppose 10 nodes in it, and we were given 3, 4, 5, 6 as our array. So first we would reverse 3 nodes and we'd be left with 7. Then we'd reverse 4 more nodes, we'd be left with 3. And then they're saying we have to reverse 5 nodes. But 5 is greater than 3, right? So what do? We simply reverse the 3 nodes, and that's the end of our linked list, the end of our reversal process, and we can simply return the linked list. So yeah, let's take a look at the logic. The logic is a little complicated to understand. There's a lot of making and breaking of links. So here we go. I'll do my best to explain it. So first, let's understand what they mean by reversing groups. So suppose over here, if we had to, these visuals were a problem where the number of nodes to be reversed are constant. So instead of an array, they would just give an integer. Suppose k equals to 2. That means you had to keep reversing nodes of group 2. But it's a very similar problem. So these visuals are quite helpful for understanding purposes. So suppose if our array only contained 2, 2, 2, 2, then what would a reversed linked list be like? Look like? We'd pick these two nodes, reverse them into 2 and 1, then we'd pick 3 and 4, reverse them into 4 and 3, reverse the 5, 6, 6 and 5, and so on and so forth. How is this different from normal reversal? Because notice that when this is reversed, the link has to be maintained. Normally, when we reverse half or all of a linked list, we change the previous and later nodes too, right? But over here, if this is being reversed, I need to make sure that it points to the reversed part of 4 too. We can't just say two points to 1 and 1 points to 3, and then when we are reversing this, one can't keep pointing to 3, right? After this second group gets reversed, 1 has to point to 4. So that is the difference, and that singular difference makes this problem much harder than a normal reversal problem. So suppose we had to reverse groups of k equals to 3. So these are the steps given over here. Let me move this diagram a bit down. So yeah, this is the reversal part. Inside the for loop is the steps we follow to reverse a node. The first observation to make is that to reverse a group of size k, we have to interchange k minus 1 links, right? So to reverse this group of size 3, this link will have to point like this, and this link would have to point like this, correct? So to reverse a group of size 3, we need to reverse 2 links. To reverse a group of size 4, we'd have to reverse 3 links. That's why notice in my for loop, I start from 1 instead of 0. So k minus 1 iterations, where k is the group size. So what steps are being followed here? Initially, we create a dummy node because we need a previous, current, and next, right? And notice that after this group gets reversed, our head originally was 1. Originally, our head is 1. But after reversal, our 1 will be over here, correct? And if we return head, then these two nodes get cut off and it gives an incorrect answer. So we maintain a dummy node which points to our current, which points to the head node of our linked list. And this initially we are modifying the first element, right? The first element link has to be modified. So of course, in any reversal problem, we need 3 pointers: previous, cur, and next. Over here, I'll say next as NEX to avoid confusion. So yeah, next is NEX or N simply. So dummy node is set to pre, 1 is set to cur, and 2 is set to NEX. So what other steps? Cur's next, okay, this is really big. Cur's next is equals to NEX is next. So what is cur? 1. NEX is 2. Cur's next. So this link gets broken. And cur's next gets set to NEX is next. NEX is next. So this link gets formed. Correct. Over here in this diagram, they've shown it over here, but I'll draw it step by step so you'll understand. So yeah, what's the next step? NEX is next is equal to previous is next. What is NEX? 2. NEX is next means this link. So this link gets broken and it gets set to previous is next. That means previous is 0, previous is next is 1. So this link gets formed. So in these two steps, what have we achieved? We have maintained a two. We wanted to break the link between 2 and 3, right? Because we needed 2 to point to 1. But if we simply reverse the link of 2 and make it point to 1, then we lose our connection to 3, right? So we maintain the connection to 3 using node number 1, and then we reverse the link of 2 and make it point to 1. So these two steps are done, correct? Now what we do, now we have to make sure like this loop goes on and on, no? So we have to make sure we are ready for the next iteration. So we are done for this node, we have to move on to node 2, right? So this dummy head, that is previous is next. What is previous? Previous is 0. Previous is next means this link gets broken. This will now point to next, NEX. So it'll point to this, correct? Over here, this is a little clearer to see. Previous gets pointed to here, because if this is the node we want to reverse next, the previous node should be over here, right? The dummy head will be used as a previous node. So previous is next, we need to set the previous, and now we need to set the next. Next is of course cur's next. What is our cur? Our cur is 1, cur's next is 3. So NEX, now this becomes NEX. NEX becomes 3. Let me just write N to avoid this khichdi. So this is N. And as you can see, this are the some of the operations taking place. This link gets broken, this link gets broken, this link gets broken, and these 3 links get formed. NEX at the end now points to 3. So that is one operation. And since there are 3 nodes, we need to perform 2 operations. So again, now we are at 2. We will perform the same operations at 2. Let me just do it over here. So what is our cur? Now we'll perform operation 1 again. Cur's next equals to NEX is next. Cur is 2, NEX is 3, recall. So this cur's next is equal to NEX is next. So what link will be formed? What link will be formed? Actually, no, cur still remains as 1, right? So cur's next gets moved to 4. So this is formed. Let me erase this link. So yes, this link gets broken and cur's next gets set to 4, because notice this is our this n represents any action next, and then NEX is next is equal to previous is next. Previous is this dummy node 0, previous is next is 2, so NEX is next is equal to 2. So what happens? This link gets formed, correct? This link gets formed. Let me erase this part. Just a second. Yeah, so those two, just ignore those 2 links. Those 2 links do not exist anymore. We have one link going like this that we saw in the first iteration. It is this blue link which I'm just redrawing, and now we have another link like this. So notice that our link list is indeed been reversed, right? Because now 3 points to 2, 2 points to 1, 1 points to 4. So we have achieved what we set out to achieve. That group has been reversed. but we need to perform some operations to set up for the next time. So this, of course, previous will move one further and next will also move one further. Let me use the eraser. This will move one further. This moves to here, and this n also moves one further. This n moves over here. Correct? So notice, if I was to redraw this, what would it be? 3 would point to 2. This would be 3. Sorry for the small drawings. 3. This would point to 2. 2 would point to 1. And 1 would point to 4. Correct? So we have achieved reversal of a group of size k. And this we saw for 3, we can go on for 4, 5, 1, whatever, so on and so forth. So that is the basic algorithm to be performed. As you can see over here, they've drawn it a bit more neatly. I'll give you a second to go through it. And this is the operation. This is what it looks like after the for loop. So previous now moves to cur, and we reduce the length by k, right? So yeah. Now let's go to the implementation. You all have understood the logic. So what is the implementation? The implementation is very simple. We need to reverse groups of size k until we do not have any more nodes to reverse, right? So to do that, we need the length of the linked list. It is not provided to us. So we'll set a variable length, and we'll use a temporary pointer to keep iterating, and we'll find the length of the linked list. And then we have two conditions. Notice in the question, it isn't mentioned anywhere that the number of elements, the sum of all the elements in the array, will be greater or equal to the number of nodes. It can be less also, right? So we need to keep a check for that. If the sum of the elements is less, that means we don't need to reverse the rest of the linked list. Just break. So yeah, we keep a check while L is less than N. That means there are more elements to be reversed, more groups present in the array to be reversed, and length greater than 0. Length represents the number of elements, number of nodes remaining, unreversed nodes remaining. So if the number of nodes to int k equals to bl, that means k, of course, is the number of nodes we are reversing in this iteration. If k is 0, move on. If k is 0, of course, you don't need to reverse anything. We move on. And yeah, simply the algorithm I mentioned. And at the end, we do not return head. That was the main part we had maintained dummies next for. We return dummies next. That's it. That was problem 2. It is a hard problem, but yeah, it is a very important problem. So this will sum up your linked list problem, basically one of the hardest linked list problem. As you can see, this is the most efficient solution. It performs better than 99.5%. So those were the two problems for today. Thank you, everyone. Goodbye.